Attention everyone. Now we are going to start the third day. We now have with us Mr. Sachinanda Babu, who will present on mission implementation and Pocket Q. Mr. Babu is a program manager at NASA's Earth Science Technology Office. He oversees the sustainable land imaging technology program and the space validation of Earth Science Technologies program. Since joining ESTO in 2016, he has focused on integrating cutting-edge technologies into future Earth observation missions, ensuring that instruments such as Landsat reflect the latest advancements. He holds an MS in physics from the University of Mumbai and MS in electrical and computer engineering from George Mason University. His expertise in technology integration for Earth observation makes this a highly anticipated session. So let's welcome Mr. Satyanarayana Babu. Over to you, sir.
Thank you. Can you hear me?
Yes, sir, I can hear you.
Okay. I'm sorry I couldn't be there. Would have allowed to be there in person and presented today's session. So, without any delay, let us get started on what I want to present. As you know that a lot of the lectures that we have heard so far, how we are implementing these reflectance measurements on small satellites. So I want to start with just an introduction that the very first small satellite from NASA was launched in 1971, along with the Apollo mission. As you can see in the picture, the astronauts are standing next to the satellite.
Is it okay if you can turn on the video?
I can't hear you clearly.
Is it okay if you can turn on the video? Everyone wants to see you.
Oh, okay. 1 second. Let me see. I just wanted to, I didn't want to turn on my video only for bandwidth reasons, but I'll turn it on. But if there are any issues, just let me know. I'll turn off.
You can turn on, be there for 5 to 7 minutes and then.
Yeah. No problem. 1 second. I'm trying to do that. Can you see me now?
Yes.
So, so as I was telling you that at least the very first small satellite was launched way back in 1971, and we have been doing that. In fact, you will hear a little bit about the Snoopy, that was a CubeSat, because how it was formulated later in the talk, as well as some information in the Pocket Cube, how to get information and things like that. I'll be giving some web links and things like that. So, when you start making a program, first thing that you look at is that what is the program impact and the technology. So, as you can see that there are 4 kinds of technologies you can look at that, and one is the incremental, just you're making some small improvements into whatever you have measured or whatever you have launched before. Or it could be disruptive, like what we did with signals. Signals were the reflectance measurement, GNSS reflectance measurement mission, which is a constellation of satellites. Or it could have a breakthrough innovation. It would be something like a SWOT mission that we have right now, NASA is flying, or it could be a game changer. Like what we are, NASA is doing right now is a deep space laser communication. So you can have multiple varieties of missions. So now coming to the point that you have heard so much about all the techniques and all that. So how does it become a space mission? To become a space mission, as you will see that I'm going to be discussing about the basics and how mission formulation happens and the realities of flight development and access to space, how you will be able to launch it, and how next mission operations, how you will be operating the mission, and then some examples, missions that I'm going to talk about it, and then closing remarks. So let's start with the basics. So fundamentals of small spacecraft, we talk in this pocket set, we call it as pocket cube in GRSS, a CubeSat, which is a nanosatellite, which could be 1 to 10 kilograms, and microsatellite. Cygnus, like I talked about earlier, that would be GNSS reflectometry, which can be 10 to 100 kilograms, or a small satellite. And then the bigger ones are called as Espering, which is about 450 kilograms of weight. So you can see that NASA has launched so many small satellites and CubeSat, and India is not far behind this because these days a lot of universities and colleges are building small satellites and launching them through PSLV launch. So as I said, it's a more of a soil moisture measurement, and as you can see that it was able to measure soil moisture over Australia. This is what it is showing here. So, you can take the example of Tempest, which was under my program. The share complete audio. Are you able to hear me? Hello? Are you able to hear me?
Yes, yes, sir.
Okay, thanks. So, as you can see, the Tempest, this was a mission on a 6U CubeSat doing the weather observations. As you can see that it had 5 different frequencies it was making the measurements, and you can see slices of 5 different altitudes where the measurements were taken. And this is a very successful mission. And past this mission, NASA has decided to launch the next mission, which is going to be 3 satellites. From first satellite to next, the second satellite is 90 seconds, and second satellite, second satellite is about 30 seconds, to see how cloud dynamics works along with the Tempest. It will have a rain cube, which is a radar of 5 different beams it will be measuring. So what we do normally is that we demonstrate a technology on a CubeSat and then take it to a bigger mission. So this has been very successful. This is the rain cube and Tempest are flying together on a mission called IEEE, which is being still built at this moment. I see that the horizontal lines, these are radar measurements, and then the disk, like that you are seeing, is the Tempest, and it was able to show that we can validate the technology on small satellite platforms. And these were 2 different platforms. One was a RainCube, the other one was a Tempest. Both were flying very close to each other, so we were able to get the measurements, simultaneous measurements of both the RainCube and Tempest. You can see this was very useful. See that this is a GameCube, how it was built, and subsystems, as you can see, everything was crammed into a 6U CubeSat. Then even was the Marco Mark Cube 1. This went to Mars since the Mars landing was on the side where we could not, opposite side of what we can see in Mars, these CubeSat were able to relay the information from the lander. This was a very important mission for NASA. And the big panel that you see here is the antenna for radio transmission. And to show very simple what parts are there inside the CubeSat, different parts, you can see that it even had the propulsion on the small satellite like this. And to give another example, this is the micromass, which is under my program, which was MIT Lincoln Lab, and this one. And this is a very small instrument. You can see that the whole instrument is a 2U bus and 1U for the passive microwave spectrometer. At the top of the deployable solar cells. So this is over 10 years past, or 15 years, you can say. There's a lot of CubeSat that have been lately being launched. So even companies like commercial companies like Planet and all, they use small satellites like CubeSats to do Earth imaging. So that is interesting to see that the small satellites can do a lot of things. So how do you, now we are coming to mission formulation. So in mission formulation, I'm going to show some examples. So as you can see, the Snoopy, which is is the PI who is with you all this week, and Rashmi was also part of the mission. So as you can see that when it was when we started thinking about the mission, when the original mission was a 1x6U and on the top and bottom antennas, but over time when we started implementing it, we ended up with a 6U with the top and bottom, as you can see the picture here. That is how. So when you start to when you finish, you would look at all the different aspects of design and how different parts can be put together and all. So from beginning to end, it can change. So from one has to be aware of the fact that what you start with is not what you get at the end of the mission formulation. So same thing with another mission, which was for heliophysics, that was done. So what we have to do is that, like for example, when we are doing any development, we want great science and have to have a balanced portfolio. So we end up with all kinds of missions, like flagship mission, we call it a big mission like JWST or missions like that, or a large satellite could be, or a medium small satellite, or a small satellite. So each one has its own advantages and disadvantages. As you can see in the bottom, in the mission, we call it the class A, class B, class C, and class D. So you have to be, when you start a mission formulation, you decide what you want your mission to be. Like, for example, Snoopy was a class D mission, which is more of like a high risk, limited budget, and also no harm to anything else that is flying along with that. So, how do we do it? So, when we come up with an idea, usually we have different groups inside NASA. They will look at what would it take to implement a mission that a PI has thought about. It could be like, as you can see that in this graphics here, what altitude we want to fly, and how much ground coverage it will give at that altitude, and then how often it will visit the same location. And a lot of these things will come into play, and based on that, we design a mission. This is like one example of that. This sunrise, this is one which is an information flight. So how would we fly multiple satellites in formation and at a distance and look at like sun, looking at sun, making it into a distributed aperture kind of a situation in this case. And later in the presentation, I'll show you how snooping came. It's flying down. So, as I said, you start with something, but when you start doing the flight development, you start realizing that what you thought was not right, and you will have to make changes to it. So, what are the requirements? You will have to start looking at the mission assurance requirement, that is quality assurance, and then how the hardware was built, and all the things are fitting together, systems engineering wise and all that. So this is very critical because when you are building a mission, you have different reviews that will take place over the life of building the mission. So what kind of reviews you will have, and you will come up with mission success criteria while developing the mission. So what is the minimum that you need to achieve to be a mission to be successful? Formal and informal review boards. So this is the you have a group of people who will be from time to time doing the reviews and then guiding you whether you are going in the right path or not. So that you have any problems that you encounter. And independent cost and the schedule estimates. This is very important because you have to cost control the environment. You will have to be able to implement something at a schedule, because schedule is also important because once you say that you are going to launch something, like present a situation like a launch vehicle availability, it gets so hard these days that, for example, if you take a transport mission that SpaceX launches next 2 years, all the transport missions are booked, although there are 3 sunsing and 1 45 inclination launch. So 4 launches a year they are all booked. Each one can take hundreds of satellites, but still they're all booked. So if you book something, you have to make sure that you have to hold your cost as well as you have to look at your schedule, and then you have to deliver in time. And managing the unexpected while you are building a satellite, a lot of things can happen. Suddenly, one part may not come in time. How you manage the schedule and that in a situation, or you might end up with some software that is like software that is not working right. So all these kind of unexpected things you have to manage. So when you're doing a program life cycle, like I said reviews, so if you're doing 7120.5, the NASA has 2 different categories, 7120.5 and 7120.8. And most of the space agencies around the world have adopted these things, but they have given their own numbers, names, however you want to call it, whether I go to NASA or ISRO or any place, they would have similar a system where you will be doing your mission planning, will be taking these kind of documents. So as you can see, that 7120.5 5 is for missions which are like class A, B, C, which are like more expensive, bigger missions. However, 7120.8 is for missions like Snoopy and others, which are normal, and basically in 17.20.8, you have a choice to tailor the requirements to the reviews and other things to your mission. So let's go quick one more step to see how 7120.5, as you can see that it requires like different approvals, like approval for formulation, you have to go through that, and then approval for implementation is how then this is one of the most important things, like KDP 0 formulation, KDP 1, KDP 2, and KDP 3. But these are very, very important milestones. All along that, there will be system requirement review, system definition review, preliminary design review, then so many different reviews. These are all reviews that you conduct for emissions. However, if you're doing a CubeSat program, it is very simple. The programs you can tailor your reviews and how you implement it, because these are done for the cost constraint and high restrictions. So this is a set of documents that are very, very important that you will have to have when you're doing a CubeSat mission, which is done under 7120.8. So you will have to do this. And one of the most important things that you have to pay attention to is that orbital space debris assessment report. This is a make or break, because this decides what kind of material that you use for building a satellite. I can give you a very simple example. When we were doing the chemistry, which you saw earlier, when we were building that, we have a titanium piece, which is 1 centimeter by 1 centimeter by 10 centimeter. It's a bar, and which is used to mount the scan mechanism. We found out that when the satellite reenters the Earth, there will be part of that will survive still. So FPP, which gives the radio license, refused to give the radio license for that mission in the last minute. So we had to scramble last minute and then come up with a plan. So the easiest way to address that problem was cut the whole bar into 2 pieces and then join it, so that when it comes back, it will work. So a simple thing like that can put whole mission off. So you have to be constantly looking at what problems come up. So you can see that mission launch manifest integration. So it is one thing is that you build the satellite, then launching itself is such a long process. You can see that how you launch, and this is for the CSLI. Basically took the satellites to space station, and from space station it deployed the satellites. However, these days it is taken to space station is becoming less and less, because of the amount of time you get in orbit is a lot less, because of the solar activity that's going on right now. So most people want to go on transport missions, which I'm sure you will later. So one of the things that I said earlier, radio frequency. This is the most important thing that you need with radio frequency license. You cannot launch your satellite and communicate with your satellite, and which takes one of the longest taking item, the longest time it takes to get the radio license. So as soon as you start your program, you want to apply for radio license, and then that will start developing your system. So that means that puts a big constraint on your mission, because you will have to, first thing you will have to do is connect. How you going to operate your satellite, because that depends on the what frequency you want to use and how often you want to make contacts depending on the ground station locations and other things. So you start with commands and then go into other technical issues. Like I said earlier, there are always there could be problems. This is one of the problems that we had on a mission. A simple PC board failure, and as you can see that in this year, we were able to narrow it down to a micro via which had not made contact, so we were having an intermittent contact, and it took a lot of work to come up with what was the problem. So this is one problem that I'm showing, but like this may have many problems. So you want to give enough time to be able to look at what problems you may encounter, and you want to be able to address those in a given time. So it takes a lot of planning, in other words. So what are the solutions? One of the things that testing is very critical. In fact, when we were working on Snoopy, we had already delivered the satellite to Houston for sending it to space station. Then we realized that there was some issue with the flight software, so we had to get the satellite back and launch it more than a year later. So these kind of things can happen, so you have to be ready for those unforeseen issues that come late in the mission. So interesting thing is that when you are launching, you have to make sure that when it is in a deploy, like a CubeSat should have a switch which disables everything in your satellite till it is launched, because you don't want anything to turn on and battery to discharge and things like that. So there's, like I said, there are so many issues that you will have to take care of. Then radiation effects. This is another thing that you have to be careful that what kind of components that you choose. And one of the most early satellites, the CubeSats, had SD cards, which were the ones which failed most. And these days, we don't use any SD cards anymore. Most satellite bus manufacturers, they use more memory chips which are soldered on directly onto the board. Then, like I said, orbital debris, and as you can see here, the number of satellites that we have today orbiting the Earth. As you can see here, each dot is a satellite, and you can see how many are there. So you have to be careful to maneuver your satellite or the other satellite, if it has a proportion, will have to maneuver not to hit each other. However, accidents do happen, and there are a lot of debris that are generated. So we have to be careful what altitude that we are launching to, and what kind of other satellites or some debris are there in that orbit. So, practical advice. One of the things that, for example, if you're building a satellite in India, then you have to worry about what kind of export controls apply to send it to US or wherever you have to send it for launching, and those things have to be also taken care of. And then to do that, there are different kinds. Like for example, in the United States, we have IEEE. ITAR is totally restricted, whereas EAR is not that much restriction, but you can still export. ITAR is very hard to export, and only certain countries you can export it to. And then the cost, like I said. So you have to start looking at the cost. How do you track the cost and different parts? Because as you can see here, there's not one line item, but so many different things you will have to take care of, not just buying the part, but you have to have money for safety and mission assurance, and then systems engineering, project management, and then parts, getting the parts, and the project management. So many things you have to take into consideration when you're coming up with a mission, and also you have to have reserves. As I said earlier, there are so many issues that can come up later in your build. You will have to have reserves so that you can complete the project. Then access to space. This is a critical thing again, like I said. So launch. So these days there are so many government and commercial launch opportunities. For example, in India you have PSLV and GSLV and all that. When they launch a big satellite, they do have what is known as an Esperling, which is just below the payload, that is the main payload that is launched. That link can hold some satellites, which I'm sure we will later how it will be launched. And so you can see that there are many opportunities available in this. However, when you are planning, you have to make sure that what altitude you're going to fly and which opportunities are available and how you can meet the schedule for those launches. Like for example, one of them is ISS deployment. These days, it is less and less. PFLV or something like that. This is the satellites are put onto a ring, and on the side of the ring, this is called as experiment. It's called experiment, and experiment has so many satellites on them, and then when you launch it, they individually, as you can see, that they individually deploy either as a group and then go to a different altitude, or at a given altitude they will be released. As you can see that this is how most of the satellites are released at different altitudes. This is like the CubeSat, how the CubeSats are deployed in space. Multiple CubeSats. In fact, one of the PSLV missions a few years ago had like almost 110 satellites because it had so many CubeSats. So you can launch many satellites at one flight, one launch. And then new this thing that this yesterday, you can see that you could deploy the ones that are mounted on the sites, or you can operate it itself as a satellite. Then there is evolving launch vehicles. We have multiple different kind of launch vehicles, just like what you have in India, PSLV and GSLV. In US, we have multiple different kind of satellite rockets that are being built or already. Then you have to be ready when you're building. You should be mentally ready for any failures. As you can see that when our three launches being done, it failed on it exploded on the launch pad. So you should be mentally prepared that just because you did all the things that your launch being the one of the last steps that will also work. So you should be prepared for such a thing. Mission operations. Now that you have launched the satellite, you are going to start wondering about how you are going to operate it. So most important thing is, like as I said, the ground station, and you would have already in your plans when you are applying for radio license, you would have already decided which ground stations you're going to use, how often it is going to be, contact will be able to make, things like that. Based on that, you will have to plan for mission operations. So as you can see here, when you launch, different stages of the launch, and once it is in the orbit, that is when you will start operating the mission. So when you look at our operation of the satellite, how do we no, well, when my satellite is passing over my ground station, it is called a two-line limit TLE, and TLE is normally is published by 28 airports in the United States, and same way, I'm sure you have ISRO giving you a exact TLE, and based on the TLE, you will be able to expect what time it is going to pass over your ground station, and will be able to contact the satellite. Like in this case, it could be right above your ground station or little away from your ground station. But you will have multiple contacts with the spacecraft. And one of the things that you look for when you are launched, first you launch, is that satellite has weakness. It will be at a certain, in a certain frequency, it will be sending a small packet of data, and you can look at that and then start making contact with the exactly when it is passing the remote from the beacon. And in some cases, people use ham operators, the maturity operators who are able to make contact to the beacon and then tell you when it passed or their home or wherever they are operating their amateur stations. Then the question comes, when you're making contact with the space, the cybersecurity, you want those, whatever commands that you send to the satellite has to be encrypted. Otherwise, somebody else can easily command your satellite and take over your satellite. So you have to be careful that you have to build cybersecurity into your mission. And then scheduling rehearsal before the launch and making sure that everybody is aware of how the operation is going to work. That is critical in your plan. Then I want to talk about some example formulation. And for this, I'm going to use Snoopy as a test case. So mission Snoopy. So let's see. So I'm sure that you've heard this in the last day and a half. So this was especially important because most of the soil moisture measurement is being done using L-band, that is a GPS signal. And so Dr. Ganson, he came up with the idea of using the P-band, which is available by somebody else's transmitting the signal, but it's not a cooperative signal like the L-band is also not a cooperative, but it is broadcasting, but it has a very set structure, whereas the P-band is very random, but we were able to find ways to use it. And that was the first thing that, okay, we're going to do P-band. Why? Because L-band only can penetrate 5 centimeters and P-band can penetrate 100 centimeters in soil to measure the moisture. The first thing was to do towers, build a small receiver and test receiver and put it on tower and see how we can make the measurements. As you can see, this was done at Purdue University tower experiments first, and then looking at that, you can see that how many cycles you get failure of the signal, whether it's the L-band or T-band, and was able to see a direct signal and then reflected signal here on the tower, and was able to prove that yes, you can do some reflectance using P-band. That was the most important thing to prove first your theory works, and then later there was experiments done at JTL to see how it works. And put on the aircraft and fly the aircraft and take the data while the aircraft is flying. Then, because I'm going to start formulating, start saying how am I going to verify my instrument is working right and I have a ground truth to do the calibration and things like that. And as you can see that multiple locations where it can be done. And then we can see that the dots, these are the places where the measurements is being done, and the circle is the footprint of the snooping, how it will be. So all these things have to be taken into consideration when you're doing con-ops and planning of the mission. So mission architecture, how then you go into the whole mission, how you set up, who is going to do what, those things are planned, and then requirements, you come up with them, then you go to the requirements, in requirements, you have to start at level 1, level 2, level 3, kind of things, who is going to be responsible for that particular one, and as you can see that, because 7120.8 as a research and technology, tailored to not harm missions, those kind of things you have to follow. Then, same thing, then we start like mission operations, how we are going to operate. That you start working on how you're going to launch, how you're going to communicate with the ground, and who all will be involved in that. Those kind of things you pay attention to. Then mission timeline, how start documenting things like the whole thing you will have planned already ahead of time for 9 months how it is going to operate. Then the mission phases, as I said, that it's a pre-launch, then take that in auto. Some point has gone in auto mode, sorry. Pre-launch, sorry. This is irritating. Let me do this just for a second. Okay. Can you see the slide now? Let me finish this one and then go to the next because it's going in auto mode for some reason. So the pre-launch and then launch and commissioning of the instrument spacecraft and then science operations, and at the end you have to also worry about disposal of the satellite that is deorbiting. So every phase has to be done. So now let's go to the pocket cube. What is pocket cube? Pocket cube is the project that IEEE GRSS is one of the sponsoring organizations. It has been done by Barcelona Polytechnic with professor teachers, and they have come up with the full instructions to how to build a CubeSat, a bucket cube, and this is a very good education tool you can use. So, what's bucket cube? See, normally a CubeSat is each unit is 10 centimeter by 10 centimeter by 10 centimeter. That is the size of each unit, and it could be 1, 2, 3, 4, 6, or in multiples. You can go as big as you can 27U up to 27U can have. Same way, the pocket cube, each cube is 5 centimeter by 5 centimeter by 5 centimeter. That means that in one unit of a CubeSat, you can fit 4 pocket cube cubes. So Barcelona Polytechnic has come up with multiple designs. So far, they have come up with 3 designs. So 3 different applications, and you'll see those going forward. So they have come up with as a part of IEEE Open Pocket Cube project. Cat 1 carries a VGA camera, this one, and Cat 2 carries an L-band RFI monitoring payload, and Cat 3 is a KA-band RFI monitor. So the address given here has the information about all these 3, as well as how to go about building one they have full instructions on that. So, as I said, Pocket Cube 1, 2, 3, these are the ones. And to support users, the two main resources. Wiki, which has all the documents, the documentation produced so far, covering the project development and testing all those documents, and GitHub, where you have software itself. You don't have to start from zero. You have a lot of software that is already developed is available on this website. And to give an example, this is the ADCS, which is the control of the heart of the satellite, which is the control of the satellite. And as you can see, that they have given the full layout of all the PC boards as well as the circuit diagram, what goes on there. All this information is available online. And another example is the VGA camera, how to build that particular camera, as you can see here. And for the same VGA program, ADCS, and this is power control board and communication board. All the designs are available online, and you can go and use those nodes, and then you can make your own satellite. For example, this is for RF application, like how to build a board, back antenna board. You can do it in your own lab. You can build your own set. And then there is if you go to our this particular website, you can see that how many open source CubeSats, Pocket Cubes are being built. These are all different places like Morgan State University, Carnegie Mellon, Yale University, and again another Carnegie Mellon, and another Carnegie Mellon, Princeton, Space Foundation. All these information are available online. You can go and look at that information and you can build it. It is a evolution from the CubeSat to Pocket Cube, and these are much easier to get launched because this is so small. It can go along with any other satellite and can be launched. Then come to the final closing remarks. As you can see that this was the 1x3, that's 3U satellite, which is doing a polarimeter. This was a CubeSat became the small sat of the year selection. This is one that my program worked on. And after this was this particular instrument was demonstrated, right now the exact same instrument is flying on a big mission called PACE, which NASA launched. It's a hyperspectral instrument, huge satellite. It has the exact same instrument there also on that mission. So then the information data, once you get the data analytics, all those things, you have to worry about how you're going to analyze the data, constellation operation, and things like that. You have to be alert. Now, as we know that Amazon, OneWeb, and SpaceX, they're all putting huge number of satellites, but it has its own problems, as you can see inside here. The Starlink satellites, when somebody is trying to do ground-based astronomy, they are not able to even make a measurement of a star, looking at the star. But so many of them keep coming in the field of view, small satellites. Future of small satellites. So there's a very good future, and we are seeing more and more small satellites being used. Mainly these days, validation technology are to show that the technology that you are thinking about is worth pursuing a bigger mission, or as an education tool. It's a great tool as education because you want to teach students how you can how we can be a part of the space, not learning, building CubeSat, launching them, operating them, and those kind of things. And I'm seeing more and more like a lot of universities in India also are getting on this bandwagon, and they're doing a lot of the small CubeSat building with different things. So I would like to acknowledge all the people who helped with me with this presentation and I can take any questions if you have any questions.
Anybody is having any questions? Yeah, anyone is having any questions? Okay, we have one such a minute.
Yeah. Go ahead.
Is there any industry partners who are working in this one? Like,
There is a lot of echo. Whether we are getting the same thing.
as you have said, that Cardinal Camps is working on this field. He is the one who is developing the CubeSat and Pocket Cube. So, is there any industries involved in this kind of work? Who is developing this kind of Pocket Cube or CubeSat for the launching for different applications?
Can you just type the thing in the chat so because too much echo I'm having.
Any industry which is working for the development of CubeSat and Pocket Cubes? Any industry?
I gave a list of all the industry pocket cube. If you go to Alba Orbit, this is the link. If you go there, you have a lot of information. Alba is one of the commercial companies. Along with that, there are many universities and companies, force of them and things like that. There are many of them are working in this area. It is becoming more and more like it is a more of an education tool, but still there are commercial companies that are interested in it. Going forward, we'll see a lot more coming along. But GRSS mainly was interested in using this as an education tool and being able to develop a whole website, VPN, and also the information about how to build a specific part for students.
Yeah, Satya, I have a question. How much budget does it require to build a Pocket Cube?
They talk a little bit slow because they're going to get.
Okay, how much budget will be expected to build a Pocket Cube?
Pocket Cube is in terms of building a Pocket Cube, you may have to spend about, I would say, in dollars, I would say about $20,000 to put in full mission. That is what 1.1.5 lakh
Yeah.
rupees. 1.5 lakh.
No, $20,000 would be
16 lakh. 16 lakh. 16
Yeah.
16 lakhs. Yeah, but today I don't that I'm talking about if you're doing in Europe or US. In India, you may be able to do it much cheaper because all the instructions are there on the website how to build. Like for example, I gave you the example of this particular one when you're looking at VGA. All the products information is given and all the information about how to make a PC board, what traces to put, all the information is there. And if you do it with students, then you can always make it much cheaper.
Yeah, that gives me a lot of information. Thank you. So, thank you so much Sachin, for your wonderful presentation, especially your Pocket Cube. I have seen, I think, last year, at excited to listen this presentation and quite useful for the students who are really interested to build any satellite or any pocket tube related stuff. So this is the end of day 2, and we'll be back tomorrow morning again at 8:30 a.m.
Can I ask you a question? How many students are there?
Yeah, here we have around 21.
Oh,
So thank you so much, Sanji, and here if can we show here?
thank you.
Thank you so much, Sanji, and is it what's the time over there?
Thank you.
What is the time over there?
Time is 5:30.
Oh my God! Thank you so much for getting up so early for all of us.
With the present situation, the way things are going on here in America, not able to um, come, but at least both Jen and Rashmi were able to make it. I would have loved to come and give a talk there, but when I'm in India next time, maybe I'll stop by.
Yes, definitely we would love to. When Rashmi told me that you are not coming, that was it was unfortunate for us.
Right now, it's very, very hard, especially we are having a lot of political turmoil going on. So it's not the right thing to travel, but at least I'm happy to see that you were able to successfully able to conduct this class.